Okay, so with the notion of alpha lengths, we can now define the PC Riemann-Stieltjes integral of a piecewise constant function. Just like with the notion of lengths, we defined back then the PC integrals of PC functions. So you can perhaps guess already what the definition is going to be. Let I be a bounded interval such that I is a subset of X and X is a subset of R. But because we are aware of the little problem we had with the definition of alpha length, we keep this condition intact. This condition means that little modification we made in that definition, the definition of alpha length. We require not just that I be a subset of X, but the closure of I be a subset of X. Let alpha from X to R and F from I to R be functions where we now need F to be piecewise constant, and a function is always piecewise constant on a bounded interval with respect to some partition, so we will have to consider a partition also. F is PC, that means piecewise constant, with respect to the partition P of I. Okay, so this is our setup. Basically, we have two functions alpha and F like this, where F is piecewise constant with the other conditions. Then we define the PC Riemann-Stieltjes integral of F. Piecewise constant integral of F over I with respect to the partition. So we denote that fact by this, by writing like this, but at the same time we want this to be for the function alpha. So to indicate the dependence of this on alpha, we write d alpha. In the notation for ordinary PC integral, we did not have this d alpha because we did not have any alpha there. Actually we had, but we are coming to that afterwards. So this is our thing, and because it is supposed to be just like the ordinary PC integral, you also can see, I mean, if you go back to that definition, that this is going to be this sum. In the ordinary PC integral, we multiplied each term, each function value in a subinterval in the partition by the ordinary length of j. Now we are going to multiply it by the alpha length of j. That's the difference from ordinary PC integral, where Cj is the constant value of f on j. Because we are already familiar with the notion of ordinary PC integral, so this is not really something new to us, but still let's see one example. Not new to us in the sense that we know the structure. consider the function f from closed interval 1 comma 3 into r, and the definition of f is this: f is 4, constantly 4, if x belongs to this half open subinterval of the domain of f, and it's constantly 2 if x belongs to this, to the rest of the interval. Okay, so this is our f. You can clearly see that f is piecewise constant on this interval with the partition consisting of these two intervals. Actually, there are other partitions also. I mean, you can subdivide this one into two parts, but at least one partition is there of this interval with respect to which f is piecewise constant. And as alpha, we are going to consider the ordinary square function. And the little condition that the closure of the domain of f, that is I closure, needs to be a subset of the domain of alpha. In this case is trivial, it's trivially true because this is the largest set in consideration. Okay, and we need to also mention the partition because everything is happening with respect to that. Also, consider the partition P of 1 comma 3. Okay, so now we have all the ingredients. So we can now calculate the PC Riemann-Stieltjes integral. So we are going to straight away write the sum. So the first C is with respect to the first subinterval 1 comma 2 times the alpha length of this interval. You have to be a little careful in writing the alpha length notation. Don't forget that the alpha length, when we write this, we enclose the interval itself within a set of square brackets. But the interval itself will also have brackets, so be a little careful. 2 comma 3 times its alpha length. This one is 4 times. And again, do not make the mistake of writing 2 minus 1. It's no longer ordinary length. Instead, in our case, this is 2 square minus 1 square plus this one is 2 times 3 square minus 2 square. So 4 times 4 minus 1 is 3 plus 2 times 9 minus 4 is 5. That means 12 plus 10 or 22. Okay, so this is one small example. There is another example, and this example will show that the ordinary PC integral of a piecewise constant function is actually a special case of our PC integral that we have defined today. Consider a very special alpha, namely the identity function on R. Let f from I, but f we are going to take as a general PC function, be a piecewise constant function on a bounded interval I with respect to, let me write WRT, the partition P of I. You may think why I write so much. See, the thing is that when you are watching this on YouTube, and also when you sit in a class and say someone is lecturing, although I do not consider these things as lectures, okay, because I am also a student, I am not a teacher. But anyway, whenever you sit somewhere and you listen to someone, you are at the same time watching some things written on board or some kind of screen. You are not just listening to what that person is saying, but at the same time you are looking at something also. And you synchronize these two things, and that goes in your mind. So if you do not see, because these things are not exactly very easy. They may look easy because we have been dealing with these things for quite some time, but there are so many things behind everything, no? So many details are there. So if you see the details again and again, they will go in your mind. So later when you try to recall, it's not something vague that, oh, so we had these things in the background and then something is being said about them. You may actually remember these things. So the more you hear them and the more you see them, the more solidly they go in your mind. That is why I write again and again. It may look boring, but it has a purpose. It's not simply to make the video very long. Remember that speed is not our aim, understanding is. Then the PC integral of f with respect to alpha and for the partition P, let's just apply the definition itself, Cj, where we understand what Cj is. Also, I do not actually write unnecessary things. We already know from the context of our discussion what Cj is, so I won't again write what Cj is. Times the alpha length of j as j varies over p. But do you remember that after defining the notion of alpha length itself, we also saw one example where we recognized the fact that when alpha is this function, is the identity function, then alpha length turns into ordinary length. They are the same in that special case. So the sum now becomes this. But if you recall, this is just our ordinary PC integral of f on I with respect to the partition P. So this tells us that our ordinary PC integral of a PC function is in fact a special case of the general, somewhat more general PC Riemann-Stieltjes integral. And the special case corresponds to this alpha. Alright, now let us also recall that after when we were developing the theory of Riemann integrals, after defining this, what did we do next? We next saw a result where we saw that for a PC function f on I, it can actually be PC, piecewise constant, with respect to two different partitions, many partitions actually, P1 and P2. But the fact is that no matter which partition you choose, if f is PC with respect to that partition, then you use that partition to calculate this integral, you get one value. You take another partition, and for that partition you calculate this similar integral, you get another value. They are actually the same. In other words, the PC integral, although it depends on the partition that you choose to calculate it, but the choice of partition is not it does not have any effect on the integral value itself. And that in fact then allowed us to define the PC integral of f over I independent of partition. It depends on partition for calculating the value, but not in a fundamental way. Different choices of partitions do not change the value. An exactly similar result is true for our PC Riemann-Stieltjes integral also. In fact, the result I am talking about for the ordinary PC integral is theorem 11 to 13. And the exact analog of this result for our PC Riemann-Stieltjes integral, we will see and prove in an exercise. This is going to be exercise 2. So we will see it and discuss it when we solve this exercise. And with this said, you assume that this is with us. We have already done this. So we can now define the PC integral of f with respect to alpha over I as the PC integral of f with respect to alpha for P, where P is some partition of I with respect to which f is piecewise constant. P is a partition of I with respect to which f is piecewise constant. Alright, so we now have this notion as well. Okay, so far we haven't put any restriction on alpha, although we discussed a little bit about this in the previous video. We said that at some stage we are going to put a restriction on alpha, impose some kind of constraint on alpha. And in fact, I think I said also there that it's going to be just that alpha needs to be monotonically increasing. So now is the time. Now we are going to impose this restriction on alpha. We now require that the alphas we are going to consider be monotonically increasing. With this requirement, we then have alpha of I greater than or equal to 0 for any bounded interval I. Do you remember that after defining the notion of alpha length, we saw one example where we calculated alpha lengths of some 2 or 3 intervals, and there we saw one instance of an alpha length being negative, and we wondered that it is so general that there is no restriction on alpha that we can have negative length, and at that time itself I mentioned that we are eventually going to put some kind of restriction on alpha. So now with this restriction of alpha being monotonically increasing, we are going to have non-negative lengths. But why? The author asks why, or more accurately, how. How do we get non-negative length? I leave this to you to figure out how monotonic increasing property leads to non-negative length. So the little argument that you should write for this actually involves two parts. Your I is a bounded interval, so I is going to be either degenerate or non-degenerate. Degenerate means I will either be the empty set or a singleton set. That is one case. In that case, you just simply calculate the alpha length and show that it's non-negative. And when I is non-degenerate, there you have those 4 types of intervals: closed, open, half open, all those things. In each case, you again think of the alpha length. You will see that the increasing nature of alpha implies that the length has to be non-negative. That's just it. And with this restriction on alpha, we can then have an analog of that theorem which gives us properties of PC Riemann integral, which we already did back then, where you show that the sum of 2 functions which are both PC also is PC and whose integral is the sum of the integrals, those things. And that result actually was, it was theorem 11 to 16. And this is also going to be handled in an exercise, and that exercise is the 3rd one, I think. Yes. This is where we will address that problem, that thing. Alright, so now the coast is clear for us to finally define upper and lower Riemann-Stieltjes integrals in exactly the same manner in which we defined upper and lower Riemann integrals. So, yeah, I better write the conditions now, because again, if you do not see all the things in one place, it's very easy to get confused. So let me start again. Let alpha from x into r be a monotonically increasing function, and f from I into r be a bounded function. Why did we not write that f is a bounded function for the other definitions? That's because there our f's were all piecewise constant, and any piecewise constant function on a bounded interval is automatically bounded because it has only finitely many values. Where I is a bounded interval satisfying this. If you feel that you can have, you can only have x as a subset of R, so there is no part to, no need to write this part. So do you see that instead of having the details in the back of your mind somewhat in a vague manner, again you can clearly see what we have with us and now what we are going to do. So we now have again two functions, alpha and f. Do not lose the gist of the thing in the mass of details. What is it that you essentially have? You have two functions, alpha and f. Then what about them? Alpha is like this, f is like this. The domain of alpha is x, the domain of f is I. And they are related like this. F needs to be bounded because f now is not necessarily piecewise constant, it may not be, but we still need boundedness. There also we needed boundedness while defining upper and lower Riemann integrals. Now we define. We define the upper integral of f over I Riemann-Stieltjes integral. So the dependence on alpha is shown like this. Now recall the definition of ordinary upper Riemann integral. It was the infimum of a set of what? Piecewise constant integrals of what? What type of functions? Piecewise constant functions majorizing f. An exactly similar thing we are going to have here, but instead of ordinary PC integral, we are going to have PC Riemann-Stieltjes integral. That's the only difference. So infimum of PC integral of G, but with that alpha over I, where G is PC on I and majorizes f on I, that's understood. So this is our upper Riemann-Stieltjes integral. Similarly, we define the lower Riemann-Stieltjes integral of f. This one involves the supremum of another set. It is the supremum of again some PC integrals, but this time G is PC on I and minorizes f on I. Okay, so exactly similar to what we previously had. And with these two notions, we can now define Riemann-Stieltjes integrability, just like we had Riemann integrability. We say that f is Riemann-Stieltjes integrable on I if these two integrals are equal. Let me write the lower one first. and when they are equal, the common value is defined to be the integral value. That's it, like before. And finally, the section is going to end now. The author says that most of the theory of Riemann integral can be carried over to this new setup, Riemann-Stieltjes integration. But there are a few results which break down. For example, he mentions that theorem 1141 part G breaks down. 1141 means there you have the basic properties of Riemann integral, not just PC Riemann integral, but Riemann integrals of bounded integrable functions. There, if you remember, you had one property where, say, you have a function f, a bounded function f on I, which is Riemann integrable, and say you extend the function f to another function j, where j is also a bounded interval containing I, and f is extended like this. I mean, small f is extended to capital F like this. It is f of x if x belongs to I, and 0 if x belongs to j but does not belong to I. In that part of the theorem, we concluded then that capital F is also Riemann integrable, and the integral of capital F on j is simply the integral of small f on I. That part. That is now not necessarily true. And then, proposition 1153 is also not necessarily true. It is that proposition where we state that if a function f is defined on a bounded interval I, the function is continuous and also bounded, then it is Riemann integrable. That's also not necessarily true now for Riemann-Stieltjes integral. And finally, there is this result also, proposition 1156, which tells us that piecewise continuous functions are Riemann integrable on a bounded interval. Piecewise continuous and bounded, that is also not necessarily true. And these results fail if our function alpha, do not forget that now we have two functions actually, f, the one you are integrating, and alpha, which in a sense you can say that we are integrating with respect to alpha, in a sense which will become clear only much later. If this alpha is discontinuous at some points, then things may fall apart, especially if alpha and f are simultaneously discontinuous at a point, then things can go wrong. We will see in one of the exercises at the end of the section, I think, where things actually go wrong if this happens. However, theorem 1151 is still true. 1151 tells us that if a function is uniformly continuous on a bounded interval, then it is Riemann integrable. Its version for Riemann-Stieltjes integral is true. Okay, so we have that. So this is where the section ends, and after that, we have exercises. So we will start solving the exercises from the next analysis video. We actually have only two more sections left. One of them has the two fundamental theorems of calculus. We are going to prove them. And the last section involves some consequences of the theory of Riemann-Stieltjes integration. With that, this 11th chapter will be over, and this analysis 1 itself will be over. After that, we will start analysis 2 with the theory of metric spaces. So these things will come at some point. Okay, so tomorrow also we have an upload, and tomorrow Let's go back to number theory again. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.